All right, so we're going to do page 3 of the packet today. So this is our introduction to sound. And sound is a wave. So we've been learning about waves, and the whole purpose of a wave is to transfer energy from one place to another. So that's what sound is. Sound is a transfer of energy from one place to another. Now it's done using a longitudinal wave. That means it requires a medium, meaning sound needs something to travel through. Now, we typically think about sound as a vibration of the air because typically our ears are in air. Okay, so what I want you to do next is go down in the description. There's a link to how our ear works. So how does our ear pick up these energy waves traveling through the air? And so it starts at about 3:08. The link should start you right there, and it goes for about a minute is the only section you need to watch. So once you finish watching that, come back here. So pause me, head over there, come back. All right, so you saw how the ear works. Okay, great. So they talk things about frequency and pitch. So pitch is what we talk about when we talk about how frequent is that wave of sound. How close together are those points of high density and low density air? Loudness is how we describe the intensity. We have also something called the sound intensity level. We use this to scale the intensity. And we're going to see how we talk about intensity and sound intensity level a little bit later on. All right. Now, I did say sound is typically done in air, but sound can travel through any medium. And so the speed of sound changes based on what medium you're going to go through. So depending on the temperature and the pressure, especially for air, that will dictate the speed of sound, and the material also makes a huge difference. So in general, the more rigid a material is, meaning like if I send a sound wave through wood versus I send it through air, the more rigid the object, the faster that energy is going to travel through it. And the more dense something is, typically the faster it's going to travel. So the more rigid and more dense, the faster that sound wave is going to travel. So if you imagine going underwater at the pool and yelling at your friend through the water, which you can always try, your friend can hear you. It's not going to be very well understood, but they can hear that sound wave transferring. Now, if somehow you were able to hold one finger underwater, one finger above the water, and snap those two fingers, and you had two friends, one underwater, one above water, the one underwater would hear the sound of the snapped finger underwater before the friend in the air, just because that sound is traveling faster underwater. They will both, of course, instantaneously see that, though. All right. So what we're going to do is we're going to use 344 meters per second. That's the speed of sound in air at room temp. So unless it's otherwise indicated as something different, this is the value we're going to use. Now, a couple other things pop into my head when I want to think about the speed of sound. Number one, Felix Baumgartner bombing out of a balloon, how many miles up, just to break the speed of sound skydiving? Why did he need to go so high up? Well, this is why. So when he went up high in the atmosphere, what happened to the density of the material? Okay, so up high, we have a low density of that air. And so we have a low density of air. That means we have a lower speed of sound. So we have that slower speed of sound. Also, the higher you go up, your density goes down. That means that there's less air resistance, and so that increases your terminal velocity. So he just had to get up high enough where the terminal velocity, getting bigger and bigger, eventually went past the speed of sound, which was getting slower and slower. And so that's why he had to jump from such a high height. Now, one other thing. We talk about this speed of sound as being something, so all those frequencies travel through it, yes, but all frequencies don't travel equally through the air. What I mean by that is some frequencies can travel further than other frequencies, and this is something we call sound attenuation. So if you look at kind of the bottom right of page 3, you're going to see that sound attenuation you'll see that sound attenuation is proportional to frequency squared. What that means is high frequencies drone out really fast compared to lower frequencies. Let me give you an example. Perhaps you've been by a lightning strike. When that lightning strike is right next to you, it sounds like a clap. There's a sharp pitch to it. You're hearing all of those higher frequencies. But when that lightning strike is far away from you, by the time that sound has gotten to you, all of those high frequencies have attenuated, have dropped off, have been scattered, absorbed. Okay? And so, as a result, that thunder sounds more of a rumble when it's far away. Now, I know you probably thought that lightning cared about you and it made different sounds based on how close it was to you. I'm sorry to break your bubble there, but yes, it is sound attenuation is proportional to the frequency squared. So if you hear loud noises at a distance, they are typically a lower pitch of that original noise just because all the upper pitches of it have droned out or attenuated out. Okay? A cool side note to this, like analogy-wise, is if you think about light traveling through the air, like sunlight, same kind of idea, those higher frequencies, the blue lights, will filter out, and all that will make it to you is the red light. So when you're looking at the sunset through a very long stretch of atmosphere, relatively speaking, you are only seeing the red lights. Well, what happened to all the blue lights? Well, the blue lights scattered out along the way so that someone over here can have a blue sky. Same kind of idea there. Those higher frequencies are scattering out. Okay? There you go.